What is a wind turbine? You could say it's this bladed thing that's stuck on a rod attached to the ground. It's like the opposite of a fan. Wind turbines convert wind energy into electrical energy. Early uses of wind turbines date back to 7th century Persia and were used to grind grain or draw water. Wind turbines are now used to provide 18.5% of all electricity in the UK. They have one of the lowest relative greenhouse gas emissions and are not controlled by some random guy in some random country. So, cheap and clean energy for the win. However, current wind turbine designs for electricity generation are excessively large. I mean, would you want a 400-foot giant fidget spinner spinning in your backyard? Also, some people think they're ugly and annoying. Do you think wind turbines are annoying?
No.
Do you think they're ugly?
No.
Do you like wind turbines?
I do.
Alright, thank you. So, a team of 6 aero students who totally know what they're doing set on task to design a mini wind turbine. The design requirements are: we have to create a horizontal axis wind turbine. The blades should turn clockwise when viewed from the front. 2. When rotating, our maximum angular velocity must not exceed 3000 rpm. 3. Our wind turbine can have any number of blades, but it has to be below 200 grams, and it has to fit inside a box with dimensions 400 millimeters. Wait, I don't know how to say that.
Millimeters.
Millimeters. No. And fit within a 400 by 150 by 100 millimeter box. And lastly, our wind turbine has to be original and bio-inspired. Our main objective is to maximize our CP at a tip speed ratio between 3 and 8, working with these restrictions.
So our first aerodynamic task was to choose which airfoil to use on our turbine. We first decided to use the SG6040 airfoil at the root tip because it had higher structural integrity, and we used SG6043 at the wingtip because it had a higher CL max and a better CL curve and aerodynamic lift. As we can see here, we can see the 2 CL curves that are two different airfoils, and hence SG6043 was a better fit for the wingtip. We optimised the wind turbine for an airspeed of 12 metres per second. We chose a tip speed ratio of 7, and then therefore with a radius of 0.37 metres, slightly larger than most groups. To optimise efficiency, we calculated our operating rotational velocity at 2,200 RPM. That produced a CP of 0.339. Discretizing the blade, we can then use some aerodynamic theory. The incoming wind speed varies along the blade length, and the Schmitz and Betz formula give the optimal angle of attack and chord length so that the airfoil produces maximum lift and hence maximum power. The blade was then optimized using the Schmitz theory over Betz. This is because the Betz theory only takes into account the axial losses downstream, whereas Schmitz additionally takes into account the downstream swirl losses due to the rotational wake. We could then implement blade element momentum theory to predict the performance of the turbine, where at each section a force balance is applied, as well as a conservation of axial and angular momentum. This allowed us to predict the amount of energy we could take from the air.
So we needed to do the structural analysis of the blade before we could approve the final design.
To calculate the forces on the blade, we used the coordinates of the airfoils at each cross-section to build up the blade, then divided it into 160 sections. Each section experiences 2 main components of force: an inertial force due to rotation acting in the radial direction, and the aerodynamic lift force normal to the disc of the blade. The inertial force was obtained by using circular motion theory, and the aerodynamic forces were obtained with the lift and drag coefficients of the airfoils used, resolved into normal and tangential components. These were converted to stresses and compared to critical values published for ABS plastic, and all around 1% of the critical value. We also calculated the deflection at the tip of the blade using engineer's theory of bending. The area and second moment of area changes along the blade, so the theory taught in first year was modified to reflect this. We found that the deflection was around 10 centimeters, which is a significant amount, but we decided that this deflection would not be detrimental to the airfoil performance because the effective angle of attack at each section of the blade would be constant.
Once we were certain that our design wouldn't break under the wind loading, we could proceed to create a 3D model of our turbine using Creo Parametric. We began with the nose cone. We opted for essentially no nose cone. This decision was to reduce the weight so we could opt for longer blades. Additionally, we discovered that the speeds we test our turbine at, and due to the size of our model, a nose cone would provide little aerodynamic benefit. We also implemented a hinge mechanism as the turbine had to be printed as a single part. Therefore, this allowed us to again have longer blades, as we could fold the turbine in half to be printed. We settled on a simple pin hinge here so we didn't spend an unnecessary amount of time overcomplicating the design. Plus, we also included some crocodile teeth inside the walls of the hub so that when unfolded, we could accurately fit them together for gluing. Next, we built the blade by importing the coordinates for our chosen airfoils, beginning with SG6040 and using a section blend to smoothly connect correctly scaled and twisted sections at equispaced points. Then repeated for our second airfoil, SG6043, extending to the tip. Then blended the blade to the cone by decreasing the chord length but ensuring it was still structurally stable. All of this was modelled out of ABS plastic. Lastly, we had to model the aluminium hub for manufacturing. However, we decided upon placing holes on the unimportant walls of the hub, as we found that this was a valid way of reducing the weight so we could extend our blades even longer.
Tom, can you explain what we've just found out?
We found out that we put the wing backwards onto our turbine.
So we had designed the turbine to spin clockwise. However, we have definitely made a mistake. In the CAD, all the pitch angles had been reversed. So in essence, all positive pitch angles are now negative, and all negative pitch angles have now become positive. So we had designed for the local airflow over the aerofoil to look like this. Unfortunately, the airflow looks like this. Thus meaning that the turbine spins the wrong way around and the aerofoil would surely stall and fail. Thankfully, we had found the mistake and spotted it in time and sent it to be reprinted, and we will definitely have a new and working turbine in time for testing.
So now we embarked on our corrected manufacturing journey, beginning with the hub. Using a CNC machine, our hub was manufactured from a section of solid circular aluminium. The hexagonal sides were milled to shape, and then the holes we included to reduce the weight were also quickly done. The hub was then parted off with a lathe, and we made sure that the hub stayed within the weight limit. In fact, there was a 10-gram reduction in weight compared to the other groups due to the holes we drilled. Once the turbine had been reprinted, the support material was removed manually as well as by using a sonic bath. Then afterwards, as a group, we proceeded to sand and glue the blades together, thus completing our turbine.
The turbine was tested on a wind tunnel at different wind speeds. As the speed increased, the curve of power against RPM was expected to move higher and to the right. However, our results didn't match what we expected. We successfully tested it at 6 meters per second, but as we increased the speed, the turbine started producing loud noises and the RPM was very unstable. So we decided not to test it at 8 or 10 meters per second. We did manage to get a curve for 12 meters per second, but it didn't have a well-defined peak and showed a lot of fluctuation. This could have happened because the blades were deflecting and twisting as they were too long and not stiff enough. This would mean that the angle of attack changed and could have led to stalling in parts of the blade, reducing leach and causing the RPM to decrease. The blade would have then stabilized and the RPM would have returned to normal, causing the periodic nature of the noises. We obtained a CP of 0.28, which was 83% of our target CP, at a TSR of 8.5. It is worth mentioning though that for the 6 meters per second curve, the maximum power delivered was impressive, and both our CP and TSR were within 20% of our predictions.
This was a pretty good result, but in making a wind turbine as large as possible within the given restrictions, we sacrificed our turbine's structural integrity. Surprisingly, our blade was optimized at low wind speeds, but this might not be practical. Our turbine tip speed ratio was higher than expected, which contributed to the structural instability. In conclusion, further designs should consider prioritizing structural considerations over purely maximizing CP output.